we see two types of modeling in general. Like one of them is the physics-based modeling, and the other one is the mathematics, like which is mostly statistical-based modeling. And like I have some quotes for the geostatistical modeling, but like in this session we are only focusing on the flow problems, flow through porous medium. Okay, and you'll see like 4 different folders: flow, logging, optimized, statistics. One is once you check the GitHub link, I will share the screen with you as well. So if you go to this link, github.com, my username and post by, so it will contain the flow first directory, logging, optimize, and statistics. There are 4 directories right now. I'm planning to add one more folder for the geomechanics, but right now it only contains 4 of them. So flow is basically deals with all types of flow that we have, like that we may encounter in fluid flow problems, like including the compressible, incompressible. They are not all complete yet, so I'm working on them and hoping that like some of you will contribute to this open source coding as well. So the other 3 are logging, optimize, and statistics. Statistics contains mainly geostatistical tools for modeling. That basically before the fluid flow through porous media, we need to generate the static reservoir model, and that static reservoir model can be generated by using the geostatistical knowledge, by doing the baryogram calculations and doing the kriging analysis, and then generating the first reservoir model to be used in the numerical simulations. So that statistics folder contains those some of those models that can be helpful for generation of the geostatistical model. Optimize contains some of the actually one of the optimization algorithm that I had a chance to work on previously, which is simulated annealing. Okay, and some applications exist in the there are some inbuilt, not inbuilt, but third-party packages for the simulating annealing as well. Well, it can be nice exercise to compare these 2 algorithms. Logging contains the computational electromagnetics tool, which can give the results of the tool in the wellbore of the oil field. Okay, like let's say we are doing the logging operation and we are collecting some of the data, some of the resistivity measurements. Let's say this logging directory can simulate those scenarios. Flow is ours. Okay, the flow directory is the main directory that we are dealing with, and right now it's a bit messy, but I'm planning to make it more more organized, and I'm hoping that again some of you will contribute to this development. There are several different topics in this flow, and basically in the single phase flow we have 7 different types of flow. Flow on the on the surface, flow through the pipe, flow through the annulus, flow through porous media, flow through pack bed, and that's the same thing for the multi-phase flow as well. For now, there are some multi-phase packages as well, functions as well, but for now we mostly focus on the single phase. And in our session as well, we are mostly focused on the single phase flow for the main session, and then we are going to switch to multi-phase and include hopefully at least in the first stage, oil and water, and then we are if the code works well, we are going to switch to gas, oil, and water. Okay. So last week we started with the single phase solution of the diffusivity equation, which basically simplifies to the Laplace equation. And we solved the steady state, which means that we don't have any transient term. We are not dealing with time yet. We're just solving the problem only once, and that's it. That's the steady state solution. And we were solving the problem in 1 dimension. Now, last week I said that we're going to start to transient problem in 1 dimension. And then we are going to move to transient multidimensional analysis. I changed the order a little bit. This week we are going to switch to steady state multidimensional analysis, and then next week we are going to switch to transient multidimensional analysis. Okay, so basically this time, like last week, we did Laplace solution in the given domain, in the given rectangular domain, Cartesian domain. We solve it in 1 dimension. This week we are going to implement the same code for the 3D simulation of the Laplace equation in the given 3D domain. First, so one of the first things is, as usual, as it's the same in the one-dimensional analysis, we need to generate the grid mesh. Basically, we need to generate the points where we are going to solve the problem. Now that's the actually, like, that seems to be the easiest part of the problem. But if you continue to work on the finite difference or any other types of computational modeling, you'll see that that is one of the most challenging and computationally overwhelming part of the issue. Okay. Now let's go over the, like, basically we went over the one-dimensional analysis last week. We are going to generate the 2D dimension in this session, 2D mesh, and then we are going to solve the finite difference in the 2D domain, and then we are going to generate the 3D mesh, and then we are going to solve the 3D. We are going to solve, like, implement the finite difference in this 3D domain. Okay, and like, to summarize, we are basically solving the Laplace equation in multi-dimensional space. Okay, so that's the goal of this session. Now, as usual, if you just go to if you just we log out from this session. Okay, if you just type BHOS on the GitHub, that's the, like, there's only one directory not named BHOS, so you can directly go to the folder that I shared with you. I will send. I already sent this link to the chat box previously, but, like, it's simple to find this directory. Now, once you have it, you can either clone, like, just copy this link that you have here by clicking on this button, or you can download zip. Okay, download zip is will be comfortable if you are not familiar with the Git installation. If you don't have Git in your machine, you can just download the zip and put it, like, after extracting the files, put it on your directory in the documents. I will suggest documents, but you can actually put it anywhere you want. Okay. For now, I'm just recommending it to put it in the documents because I'm going to do the same thing. If you're familiar with the Git, just copy this link and then go to the your command prompt. You can just type the CMD in your search box, and then this command prompt will open, and then you can just go to the documents file. Okay, and then you can just type git clone and paste the link that you copied. Okay, after you do that, it will start automatic installation, like, it automatically download all the files that we have here. After you do that, I already did that, so I have the BHOS file. That's why I'm not clicking enter. So after you do that, you will be able to enter the BHOS script. Okay, if you don't see any error message, it means that the download was successful. Okay. Now the other way is just to download the zip, and after downloading, you can just extract the files. Okay. It shouldn't take that much of time. It should be simple. Okay. Let me show this way as well. So after downloading, you just need to extract the files. Okay. And then by clicking on the BHOS main, you can just copy this directory to the documents and name it as a BHOS file. Okay, just remove the main part. Okay? If you see the main attachment, just remove the main part. And then if you go to the BHOS file, the flow directory is the main directory that we are going to work on. Okay, and we have this analytical script. These two are the main scripts that we need in this directory. Okay, analytical and computation. Computation is basically contains all the information that we need, all the mathematical operation that we need for the numerical calculation that I'm showing here. And analytical solution will be showing, actually it contains already, but we're not going to use it for today's session. So basically it will contain the one-dimensional transient solution, and also it will contain the backlit average solution, which will be necessary for the validation of our multi-dimensional multi-phase simulator. Okay, they're going to inject the water and to the oil existing reservoir, and then we are going to compare our numerical and analytical results. Okay, and this analytical will contain the backlit average solution. Actually, it should be somewhere here. Buckley-Leverett solution. So this immiscible displacement solution is the Buckley-Leverett solution that we will need for the validation of our simulator. Now, this computational, as I said, for now, it contains only the finite difference analysis. In the future, I'm hoping that I will be able to implement the finite element as well. It just takes time, okay? Now, there is some... Okay. This finite difference implementation, I just made it to make it in a most efficient way, okay? But I will be working on it, try to improve it further. But for now, its computational capabilities are quite sufficient. In the yesterday's session, in the class, in the fluid mechanics class, we just did the simulation of the 1 million grids, okay? And like after about like 30 seconds, 30 seconds or 1 minute, we got the result for the finite difference implementation in two-dimensional analysis with the 1 million grids, okay, which is exciting. Now, one of the things, as I said, we need to generate the mesh, which is going to be a regular mesh in the Cartesian domain, and we can have three-dimensional domain, okay? And the other thing we are going to implement the central differentiation in that domain, okay? So basically, the order is 2 by default, okay? We are solving the Laplace problem. That's why the order is going to be 2. Then we need to implement the boundary condition. As I said, there are 2 types of boundary condition: Dirichlet boundary condition, Newman boundary condition. And our code should be able to implement them both on the same time. Okay, we just as an input will say that, okay, on the x right hand side on the x-axis, I want to implement the Newman boundary condition with gradient to be equal to 0. And or I want to implement the Dirichlet boundary condition where the pressure is equal to 50, for example, or maybe pressure is equal to 1000 psi. Okay. Now, at this stage, there is some conceptual issues that we need to understand. For now, we don't have any well. Okay. Usually, in the reservoir simulations, we have the boundaries on the edges which implement the Newman boundary condition. Okay. There is no Dirichlet boundary condition on the reservoir boundaries usually. Okay. That's a typical scenario. Like if we have the reservoir on the boundaries, we're just implementing the Newman boundary condition with gradient to be equal to 0. Gradient to the normal direction to the edge of the boundary to be equal to 0. Okay, that's a typical implementation. Now, the other boundary conditions are implemented through the wellbore. For now, we don't have any wellbore. Okay, we are not defining the location of the wellbore, and we are not constraining the simulator with the wellbore conditions for now. We just have boundaries, and we are deciding on the boundary conditions on the edges of the reservoir. Okay. Now, in terms of boundary conditions in the wellbore, when we will implement this wellbore conditions for the future, we'll just implement, like, we will need both the Dirichlet boundary condition and Newman boundary condition, because we will need both constant flow rate solution and we will need also constant pressure solution. So these 2 different types of wellbore condition we may have in the wellbore in reality will dictate us to use both Dirichlet and Newman boundary conditions. So that's why I'm keeping this code simplified and capable of using both types of boundary conditions. Okay, but like, please don't forget that for now we don't have any wellbore. We just have reservoir. We're implementing the boundary conditions on the edges. We can technically implement the Dirichlet boundary condition in the reservoir edges, but in general, in the reservoir simulation, we usually implement Newman boundary condition on the edges of the reservoir, because that's the reality. Okay, we can't put the constant pressure on the edges of the reservoir, because we don't have any control on the pressure on the edges of the reservoir. Now, so this is the finite difference in the computational package. Then if you go to the test directory, there are some of the tests that I already just wrote some of them in order to test whether the mesh generation is all right and the finite difference analysis is all right or not. So one of the, like we said, like last week, we implemented the Laplace equation in 1D dimensions. Now we are going to start the 2D analysis. So first we need the 2D mesh generation. Okay. Now there will be some slight modifications because there was some changes in the code that I made. Okay, there is no mesh anymore in the computation package. Okay, it's all inside the finite difference. So that's why I'm renaming this as a mesh. Okay, and all these Cartesian are the function and methods of the finite difference class. Okay, that's why I'm calling this. Let's keep the name as grids. Okay, I think it makes sense to have the grids with the finite difference analysis capabilities because we are using the element information to do the finite difference calculation. Now, for the other thing is we are generating the Cartesian grids. Okay, let's say that I want the number of the grids in the x direction to be equal to 5. Okay, and the number of the elements in the y direction to be equal to 6. Okay, now so this is the one of them is length, the other one is the number of grids in that direction. Let me check which one is which. So basically, first one is the length, the second one is the grid number. Okay, length and grid number. Okay, so that's why I'm going to change this one, number x, and this one is going to be number y. Okay, and since we are doing one-dimensional analysis, I'm keeping this one. Okay, I want to generate a 2D grids. Okay, but I have some dimensions in the third direction, which is z-axis for now, in this case. But we don't have any discretization in this direction, which means that we have only one element in that direction. Okay. Now, these are the boundary conditions I'm implementing for now. For all of them, I'm assuming that I will, for all edges of the reservoir, I'm implementing the three-sheet boundary condition with the specified values of the pressure at the edges. Okay, here I'm assuming that the pressure should be 50, and let's make it more reasonable. Let's make it 100. Okay, physically meaningful. Let's make it 0. Okay, and then let's make it 30. Okay, and then let's make this one as 200. Okay, because pressure value cannot be negative. I don't want to get the negative value. Okay, now so this z index is just the layer in which direction the information will be shown. Okay, so that's why the z index is 0 for all scenario in this case, because we are doing the two-dimensional analysis. Okay, we have the layer with the numbers specified as 0, 1, 2 up to number of grids in the x direction multiplied with the number of grids in the y direction. Okay, now I can generate the mesh now. Okay, let me see if there is no error. So okay, let me do some little modifications here. I don't want to deal with this for now. I just commented out this testing function that I was calling inside of the finite difference, and I commented out this calling session. And for now, I'm having this issue with the referencing directories between each other. Okay, I will fix this issue. I will try to fix this issue until the next session. But for now, you just need to comment out these two lines that you see here. First, you need to comment out this from flow test import test 3D finite difference, and the second one is you just need to comment out this session, which is under the main, after the main session of this script. Okay, it doesn't have anything to do with the flow of the general solver that we have for the finite difference. Okay, just comment out these two, and hopefully this time it will work. Okay, now we have 5 grids in the x direction. Okay, which 1, 2, 3, 4, 5 grids are in the x direction, and we have 6 grids in the y direction. And if you count, you'll see that the number is 6. And for all of them, we are assuming that the delta x is equal to 1 and delta y is equal to 1, because I have the same information for the length as well. Okay, now this is just the visualization, 2D visualization. So what I need from the 2D map. First, I need the grid IDs itself, like 0, 1, 2, 3. I don't have like each of the elements that you see here has a unique number. Okay, this 0, I can't have any element other than this element with the same index number. Okay, there can be no element in this domain with the same index number. It shouldn't necessarily start with 0. Okay, it can start with the 100. It doesn't have anything to do with the basically, it can be any number, 100, but that number should be unique in this domain. Okay, that's one of the information I need for the for this geometry, basically. Okay. Then second thing, I need basically neighbor information. Okay, I want to know which grid I have in the positive x direction and which grid I have in the negative x direction. Also, I have like upper neighbors as well. Like I want to have like information which grid is in the upper in like positive y direction and which neighbor is in the negative y direction, because I'm sharing these borders with them. And also I want to accurately, like exactly know, because of the numerical computations I'm doing because of the Laplace operator, I need to know exact neighbors of this each element. Okay, that's why I'm importing, I'm calculating inside of this grid Cartesian, I'm calculating the grids IDs. Okay, and that ID gives me information. Let me run it again and show the plot as well. So that grid ID gives me information, exact information about the element itself. In the first row, I have the element number itself. And in the second row, I have the neighbors in the positive x direction, sorry, in the minus x direction. Okay, if you check, for example, 8, now the element in the minus x direction is 7. Okay, you see the 7 value here. Okay, the other information I need is the positive x direction. Okay, which that one is 9. Okay, so the other thing I need is the minus y direction, which is 3, and positive y direction, which is 13. Okay, for this 3, for this 8th element, I have the 4 neighbors. Now, about the z-axis, we said that we are doing everything like our computation in the 2-dimensional space, but actually the mesh generates all the 3D grids. Basically, we don't have any like we have our grid number in the z direction is 1, so that's why we don't have any neighbor in the z direction, positive in z direction and minus z direction. So that's why for the positive z minus z direction, I'm specifying the grid ID of itself. Okay, I'm just saying that it's 8 because it doesn't have any neighbor, so I'm just specifying the value itself. And that's the same thing for the positive z direction as well. Okay, I'm just keeping the same number, I'm not changing it. Now that's the same thing for the elements which doesn't have any neighbor in the minus x direction. For example, 5. Okay, it doesn't have any neighbor in the minus x direction, so that's why I'm keeping its x neighbor, negative x neighbor, to be itself. Okay, so that's the main thing I want from the grids. Like this is basically called the connectivity map. Okay, and that's the main thing I need for the calculations in the finite difference. Okay, if you can generate this connectivity map for yourself, you will be able to do all the remaining computations with the finite difference. Okay, so that's the main thing in this computation. Now, so I have this information now. Okay, I can generate the mesh in 2D, and I need to check whether I can solve this problem. Okay, now grids. The remaining part of the script is just running the script and trying to visualize the plot. Okay, this is the plot that's generated. Okay, this part of the code is only for the generation of the plot that you see here. Okay, this is the plot that we are generating with these lines. Okay. Otherwise, we are only calling the grids Cartesian, and we are specifying the length in the x direction to be 5, length in the y direction to be 6, and length in the z direction to be 2. Okay, and number of grids in the x direction is 5. Number of y in the number of grids in the y direction is 6, and number of grids in the z direction is 1, because we are doing 2-dimensional analysis. Okay. Now let me close this one and let me go to the test to the finite difference. Okay. Test 2D finite difference. Okay, let's try to modify this one as well to random. Okay, now we like in this case I'm calling it solver. Okay, I'm naming it as a solver. Now solver finite difference. Okay, I'm calling this Cartesian again, and I have the number of x, number of y, and number of z. Okay, I'm sorry, this one is 3D. Okay, let me go to the 2D finite difference. So I have number of x equal to 50 and number of y equal to 50 as well. Okay, I'm just again doing that modification that I did for the previous case. Okay, finite difference, and I'm naming it as a grids, and I'm keeping it as a grids Cartesian. And this is the length of the reservoir in the x direction, length of the reservoir in y direction, and length of the reservoir in z direction. Okay, and again, I'm doing the two-dimensional analysis. That's why I'm keeping it the number of number of grids in the z direction to be equal to 1. Okay, and my boundary conditions on the left-hand side of the reservoir, where the x equal to 0. Okay, it's Dirichlet boundary condition with the pressure value to be equal to 0. Okay. I'm just saying the pressure, but actually, like it can be any other physical term. But since we are going to solve the pressure distribution in the reservoir, for now I'm calling them pressure. Okay. Then X max is the boundary condition on the right-hand side, and I'm assuming that the Newton boundary conditions are implemented. So gradient of the pressure with respect to basically gradient of the pressure with respect to x at the x equal to reservoir length in the x direction is equal to 0. Okay, and then I have the Dirichlet boundary condition in y min and the Dirichlet boundary condition in the y max with the pressure value specified to be 100. Okay, now I don't need to call this one anymore, and I can just go with the grids. Okay, I named it as a grids, and these are the and this is the b vector that this line I'm calling just because I want to generate the right-hand side of the equation as well. Okay, so the right-hand side of the equation in the Laplace, it's usually 0. Okay, it's usually like regularly filled with 0 because I'm solving the Laplace problem. Basically, Laplace of p is equal to 0. That's the equation I'm solving. So the right-hand side of the equation is 0. So I need to fill the b vector with zeros. And then I'm going to alter it a little bit just because of the boundary conditions, okay? Because on the boundaries, they are not 0 anymore because there are some neighbors that I'm missing for some of the elements that I have, okay? Now, if I go with the grids everywhere, and if I implement the boundary condition, and then if I type the grid solve, now this should be the grid center, and solver grids. Solver needs to be replaced with the grids. Okay. Those are the changes I need to do because of the last modification. Let's see whether it works. So this is the pressure map I'm going to get. So basically, in the simulator, I was implementing the Dirichlet boundary condition on the y mean. Okay, y mean I have the pressure value equal to 0. So you see the solution is the same. We have the 0 pressure value at the y mean. Okay, y max I have the Dirichlet boundary condition equal to 100. You see the upper part of the reservoir is going to 100 as well. Okay, so this like basically shows that like we're doing this we're just checking the code whether it makes sense or not. Okay, we're making a sanity check, and we see that whatever boundary conditions we're implementing on the y min and y max is like looks all right. Okay, and also we are looking at the boundary condition we have in the x mean, which is 0. Again, we have the 0 value here in this direction, and also in the x max we're implementing Newman boundary condition. That also makes sense because I don't have any variation in the pressure in the x direction at this x max. Okay, so like it seems to be a reasonable solution. Okay, now that's a sanity check. We need to have some analytical validation as well. So for the further steps, I'm going to include the analytical solution in the 2D domain of the Laplace equation for the rectangular case. Then we will be able to compare that scenario as well. Okay, but for now we don't have any analytical comparison. in this packet. In literature, we have the analytical solution for the Laplace in 2D domain for the rectangular case. Okay, and that can be achieved with the Green's function. Okay? But for now, we don't have it implemented in this packet yet. Now, so basically, that's the map I'm generating, and you saw already the points where we're solving this problem. Okay, you see the grid numbers for the decreased number of the grids. You saw the solution. Okay, now you can go over the script again after this session. I'm going to update the PostPy package that I have in the GitHub with the changes that I made in this session during this session. So you will be able, if you download it afterward, you will be able to run the script, and you shouldn't see any error message. You should be running all right. Now, this is a two-dimensional analysis. Okay, now we can solve the two-dimensional Laplace equation in the given domain. Okay, in the given Cartesian domain. Now let's go to the switch to the three-dimensional analysis. Now for the three dimensions, so again, we need to specify the number of grids in the x direction, y direction, and z direction. Okay, this should be different than one. Okay, that's why we're saying that we are solving the problem in 3D. Okay, now if you run the script, let me comment out this one. Actually, delete that line because we'll not need it anymore. Now, these are the points in space where we are solving the problem. Now, our simulator, we switch to the three-dimensional analysis. So that's why there are some neighbors in the z direction as well. Okay. So in our grid map should include that information as well. Okay. You see, there is an elevation difference. This is the zero index value. We have the x-axis here. Previously, it was labeled as 0. And the neighbor in the positive z direction is not basically 1. It's the indexing goes in this way, actually, based on this mesh generator that we have in this packet. Okay, 0, 1, 2, 3, 4. This one in the positive, like increase in the y increment, the y direction, incremental increase in the y direction. Will be the next thing that we are going to go after the x direction. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, and then again we're going in the positive y direction, and it's going to be 8, 9, 10, 11. Okay, only after then we're going to switch to the 12, 13, 14, 15. Okay, then in the, like if we are done with the first layer, we are going to switch to the second layer of the reservoir. Okay, these are the three-dimensional points that we are generating in the space in order to solve this problem. Okay, these are the grids, the same way that we did for the 2D analysis. Now, if you check the grids ID, you'll see that, well, basically we have some changes different, like this Z, fifth and sixth column, which are these two columns, are a little bit different than what we used to see for the two-dimensional analysis. In the two-dimensional analysis, it was 0, 1, 2, 3, 4, 5, and the same numbers indexing that we have for the first column, which was the index of the grid itself, that's where we are doing the computation. Now it's now for the first layer, we have only positive neighbors. We have neighbors in the positive z directions only. Okay, and those numbers are 12, 13, which are different than the idea of the grids that we are dealing with at this step, at this computation step. Okay, this we have, like, since we have two discretization, two element discretization in the z direction, we are going to have only one layer which have the upper neighbors and one layer which have only lower neighbors. Okay, so this grid ID information contains all this information, and again we're basically implementing the same idea that we have for the 2D in the finite difference algorithm. Okay, now let's go to the 3D finite difference. So basically in the I have increased the number of elements in the x direction, y direction, and z direction to get a better visualization. Okay, and if you like import everything, if you do everything the same, you just call the solver finite difference and then specify the number of elements, and we are specifying the grids to be regular, because for now this package works with the regular. Actually, the mesh generation works with the regular, but finite difference scheme can implement the irregular spacing as well. Okay. The only problem is the mesh generation part. And for now, sticking to the grids, regular grids looks fine to me. And again, as I said, the mesh generation part is the most computational overwhelming part. Okay, that's why it's not straightforward to implement their irregular mesh generators directly in the finite difference class. Now, we are doing everything same, except at this third stage, we are going to generate a 3D visualization of the pressure values. Okay. And this is the plot that we are getting. I'm doing the previously we were for the 2-dimensional analysis, we were getting the contour plots of the figure. But for this case, I'm just making a scatter plot. Okay. For now, this was the best way of visualizing the result. Okay. Again, if you check the boundary condition, if you do the sanity check, we have at the x min, we are implementing this Dirichlet boundary condition with 0. Okay, you see this color bar here, and x equal to like basically x min is the left hand side of this grid, and you see that those colors are dark, which means that they are equal to 0. Okay, and for the x max, we're implementing Newman boundary condition. You see that whatever value we have on this elements is the same as almost the same as the elements that we have on the neighbor ones in the -x direction. So which means that this Newman boundary condition is implemented correctly as well. Now for the y mean, where the y is equal to 0, we have the Dirichlet boundary condition with 0. Okay, we have the elements with the dark color, which means that it's 0 based on this color bar scheme that you see here. Okay, and for the y max, we're implementing the Dirichlet boundary condition with 100 value. Okay, and you see the result is the same. Okay, we have the light yellow color here on this y equal to reservoir length in the y direction. Basically, there is the values are light yellow, which means that and the color bar shows that those light yellow colors are equal to 100, which seems to be all right. And for the last two boundary condition we had in the z direction, basically we're implementing the Newman boundary condition in the positive z direction and minus z direction in the upper and lower surfaces of the Cartesian. And you see there is no variation, almost there is no variation in the z direction. Okay, actually there is no variation in the z direction. And that's the typical, like basically this boundary condition means that there will be no changes in the pressure in the z direction. So, and you see from this plot, as you see from this plot, there is no difference in the surfaces, like at the z equal to 0, and also z equal to reservoir length in the z direction. Okay, so which means that there is no variation of the pressure in the z direction. Like this makes sense now, as like this 3D solution makes sense, which increases the confidence in the solver. Okay. These are all solutions that we have for the Laplace, and like as I said, in last week we solved the Laplace equation in the 1D domain. Now this week we solved the Laplace equation in multidimensional space. Now next week we are going to switch to the actual diffusivity equation, which is the transient diffusivity equation that we are going to solve. Like basically we are going to have the time steps, and which will be a little bit more computational overwhelming, because we are going to will not be able to solve any more 1 million by 1 million cells. Okay, we are going to have the time steps. Based on the time steps, we'll need to have decreased number of unknowns, because we'll have additional iteration in the time axis. Basically, having time means that we have the fourth dimension, and that fourth dimension increases the computational time. So we are done with the single phase steady state one-dimensional analysis. We are done with the single phase steady state multi-dimensional analysis. Next week we are going to start to the single phase transient problem in multi-dimensional space, and then hopefully we are going to switch to the multi-phase transient multi-dimensional analysis. Okay, do you have any question from this session regarding these solutions that we have?
Hello everyone again. If you guys have any questions, you may just unmute yourselves and ask it straight away, or drop them into the chat. All right, seems like we do not have any questions.
Okay.
Thanks a lot for the session, Javid teacher. It's been very informative, and it is actually very cool to be able to plot these graphs, in my opinion. And I believe most of our attendees think the same. And thanks again for everyone who joined us today. And we will be waiting for you at the same time and at the same date the next week. So thanks again to our presenter. And if you have any questions, you can address those questions directly to any board member of SPE BHOS, and we will help you contact our presenter, or I will be dropping the email of our presenter to the chat box, so you can have it from there as well. So if there are no questions left, I would like to close the session.
Thank you very
Thanks
much.
again a lot. Uh, Thanks again a lot to our presenter for this informative session, and wish to see you guys in the next session.